All right. So section 5, we're going to look at the multiplication law of probability, and I'm gonna bring up a couple things here. I'm going to talk about this formula, introduce a couple words for us, and again, just like we did last time, I'm going to start with a table here and a couple scenarios. So first scenario here, I'll say A, C, B, and D, and let's get some values here. So 2, 4, 5, and 9, and get the totals. 7, 13, 20, 6, and 14, right? Okay. So a couple questions here. Let's find out what's the probability of A. 7 out of 20. What's the probability of B? God bless you. 6 out of 20. Okay. What's the probability of A given B? Okay, so 2 out of 6. Good. You good with that? We can reduce these, that's fine. So 6 out of 20 would be 3 out of 10. This would be 1 out of 3. What's the probability of B given A? Two out of 7. Good. What's the probability of A and B? Two out of 20, which is 1 out of 10. Okay. Now, here's what I want you to see. What happens if we multiply these two together? What's 7 over 20 times 2 over 7? What does it reduce it though? We get 7 over 20 times 2 over 7, which is 2 over 20, which is 1 over 10, huh? So I get this. What happens if I multiply these two together? What's 3 over 10 times 1 over 3? I get this again. Don't I? Get 1 out of 10. And what about if I multiply the probability of A times the probability of B? Do I get 1/10? Is 7 over 20 times 3 over 10 equal to 1 over 10? You get 21 over 200. No. Okay. So there's a formula. The probability of A and B, like people want to say, well, that's the probability of A times the probability of B. Not necessarily. Not going to happen here, is it? But it's, if I wanted to start with the probability of A times something, it would be probability of A times the probability, yes, of B, but given that A happened. Okay? That's what we see there. Also, we could write that the probability of A and B is equal to the, say maybe I wanted to start with the probability of B. Then what would I have to multiply it with? The probability of A given B. Okay? So if you want to find the probability of A and B, then we're going to have to use something like this. Now let's relate it to what we had before. We had the probability of A or B, right? What was the formula for that one? minus. Okay, so now notice we got that and b right here. So now we can expand this formula a little bit more. We can say it's the probability of A plus the probability of B minus the probability of A, finish it, B given A. Okay? All right. Now, let me contrast this with another scenario. Okay. Let's go A, C, B, D. And say 2 and a 4 and an 8, 12. Let's say this adds up to 10. This adds up to 16. This is 26. We get 20 here. We get 6 here. Okay. What's the probability of A? 10 over 26, good, which is 5 out of 13. Okay. What's the probability of A given B? A given B, let's see here. So 2 out of 6, 1/3. Okay, what's the probability of B? Oops, probability of B is 6 out of 26. It's 3 out of 13. And the probability of B given A? So out of all the A's, so 2 out of 10, right? 1 out of 5. And this is not working the way I wanted it to. Okay. Bear with me here. I'm going to adjust some stuff because this is not going to support my point here. We're doing it right. It's just not the case that I wanted to look at. Let's do this. Wanted it to be. Yeah. Let's see if this works. Let me check here. No. Okay, I'm gonna need more time to create this example for you. Okay, I will come back to it. This right now will serve us for what we need to do, but I'm gonna come up with that contrasting example. I just can't come up with it on the spot. Okay, and we'll continue. So let's look at some. Let's jump into this problem here. So we need to know a few things about cards. Okay. And I listed what you need to know. And some of you are really familiar with cards and some of you are not. And if you're not, I encourage you to pull out a deck of cards this weekend and play some cards. Get familiar with the deck, all right? What's that? You have some in your packet, so you know. So a standard deck has 52 cards consisting of 4 suits, and they're all equally divided. You got your hearts, diamonds, clubs, and spades. Each suit has 13 cards. So 13 plus 13 plus 13 plus 13 makes your 52. These are the 13 cards. You got ace. You got the numbers 2 through 10. You got your jack, queen, king. Half your cards are red. Those are your hearts and diamonds. Half the cards are black. Those are the clubs and spades. And then jacks, queens, and kings are considered face cards. Ace is not a face card. Okay, so that's what you need to know. And again, if you're not familiar with cards, I encourage you play some cards this weekend. So okay. So I'm going to do a few of these with you. Let's start with D. We're selecting one card from a shuffled deck, and we want to know what's the probability it's a jack given it's a club. All right, probability it's a jack given it's a club. So this is a conditional probability, so this is going to be our denominator out of the clubs. How many clubs are there? Hold on 1 second, guys. Okay, so jacks is, so how many clubs? You got 13 clubs. And out of those 13, how many jacks are there? 1. Okay. Hello. Yeah, right there. So what if I ask you what's the probability that we just get a jack? How many cards are there now? 52. And how many jacks are there? 4. And if we reduce that, we get the same thing. So in this case, it didn't matter that I put that extra requirement on or that extra condition, right? And when you have things like that, so if the probability of A is going to equal the probability of A given B, which is a scenario I was trying to create with the table, but didn't come up with that, but I will come up with that for you. If that happens, then we say events A and B are independent of each other. So in this case, the getting a jack or getting a club, those are independent of each other. Or another way to say that is, it didn't matter that I put that condition. We still got the same probability. They're independent of each other. They don't depend on one another. Okay. Next one I want you to try is F. Find the probability of getting an even numbered spade. You already have it? Yeah. There's only one else. You said earlier that. No, I need to fix that. Okay, thank you for pointing that out. So face cards are not a value. Don't count face cards as values. So just the 2 through 10 is what you're going to count. Okay, I have some errors there. Okay, thanks. Thank you. Okay, so what's the denominator going to be, guys, on F? It's out of how many cards? 52. And out of those 52, how many even spades are there? 5. There's the 2 of spades, the 4 of spades, 6, 8, and 10 of spades. Those are the 5 spades. 5 out of 10. 5 out of 52, sorry. All right, let's do one more together. Let's do part K. A king or a spade. So we're doing part K. Find the probability of getting a king or a spade. Not really. So what's the denominator? It's out of all the cards, 52. So how many spades are there? There's 13 are spades. How many kings are there? 4. But I'm counting something twice because out of the 13 spades, one of those is the king of spades. And out of these 4 kings, one of them is the king of spades. So I counted him twice, so I need to take away 1. And so we get 16 out of 52, which is 4 out of 13. You okay with that? Okay. So I'll leave the other card ones for you to do. Let's now skip and let's try number 3. Okay. So number 3 says after shuffling a standard deck of cards, no jokers, so it's 52 cards. What's the probability that the top 2 cards are both clubs? Okay. So this is equivalent to asking, hey, what's the probability that we get a club? I'll put C for club on my first pick and a club on my second pick. So that's what my notation means. And there's the formula that we were kind of working with when we did the table. We saw that that would be equal to the probability of getting a club on my first pick times what? Remember how we did that? If it's and, you guys were on it before. Are you forgetting? Probability of C2 given C1. There we go. Good job. All right. So let's try this. All right. What's the probability that the first one I pick is a club? There's 13 clubs out of 52. Okay. No jokers. Okay. Now, what's the probability that the second one's a club, given that I already picked up a club? There's 12 clubs left because I already picked one up out of. I already picked one up. 51. Okay. You see what I'm doing now? All right. So now I'm reducing this. Okay, so I could divide by 13 and get 1/4. I could divide by 4 and get 3 here. I could divide by 3 and get 1 out of what? What's 51 divided by 3? Is it 17? So 1 out of 17. All right. What's that? What I reduced it. So it's 13 out of 52 times 12 out of 51, and I just kept reducing it until I got 1 out of 17. So I divided by 13 to get 1/4. You okay with that? I reduced it. Okay. Let's now take a look at number 6. Suppose you have randomly drawn a 6, 7, 9, and 10 from a standard deck of cards. What's the probability that your next draw will be an 8? Yeah, some of my answers are off. You guys are going to have to help me with my answer sheet. Okay? Yeah. Sorry. Okay, so 6 is asking this. What's the probability I get an 8 given I already drew a 6, 7, 9, and a 10? So, how many in the top? How many 8s are there? There's still 4 8s out of 48 cards left because I already picked up 4 cards, right? There were 52. There were 52 cards and I picked up 4 cards, so there's only 48 cards left. And so that's going to be 1 out of 12. That making some sense? All right. Let's, I want to look at this tree diagram with you guys and talk a little bit about tree diagram. Okay. So this is on number 10. I'm going to zoom in on the tree diagram. Okay. What do you guys think this 35% represents? The probability of what? The probability of getting sunlight, okay? And then the 65% would represent the probability of, I'll put NS for no sun, okay? You guys okay with my notation? All right. What do you think this 80% represents? The probability that it grew, but I can't say that because there's the grew down here as well. It's grew given that it already had sun. You see how that works? It's not the probability that it grew and had sun. Careful. It's the probability that it grew given that it had sun. How would I find the probability that it grew, it had sun and it grew? What's that? Okay, we'll get back to that. No, not. What's 20% going to represent? Okay. Probability of no grow given sun. Okay, good. What's the 15%? Probability grew given no sun. Okay, good. So you're getting a sense of what's here, right? So let's try to answer some questions now. A says, what's the probability that it grew given no sun? We just labeled it. It's on the. We just read it from our tree diagram there, right? All right. B says, what's the probability that the plant was both in the sun and it grew? So this would be the probability that we have sun and it grew. All right. Think about your formula. What times what equals this? Probability of sun times probability of G given S. So if I want to find both of these, I need to multiply those two numbers together. Which makes sense, right? A little bit, maybe? Okay, so I need to multiply together the 0.35 and the 0.8. I'm just changing my percent to decimal. And what do we get? Point what? 0.28, okay. So there's a 28% chance that I make it all the way. All right, good. Because you know it's not going to be 80%. That some of you said this is the probability that grew and sun. That's a high probability if you have all these other cases, right? This makes a little more sense. It's a 28% chance that you'll end up with one of these 4 cases. Okay. Let's try C. What's the probability the plant had sun and grew, or it had no sun and did not grow? Careful where the ands are. Careful where the or is. You guys see what I'm doing here? So I'm finding individually what's the probability of sun and grow, which we already did. I just copied it down again. And then I'm finding a new one for us, the probability no sun and no grow, which is 0.65 times 0.85. Anybody get that? What'd you get, Leah? Yeah. That's good. No, let's leave it at that. Leave it there. So then we need or. Okay, now when you think of or, that's when you ask the question, are these mutually exclusive? That's an important question whenever you're doing an or problem. Are these two events mutually exclusive? Mutually exclusive means they cannot happen at the same time. So one route, can I take one route and end up in the same destination? I can't. If I take one of the routes, I can't end up here at the GRU and or down here, right? Either one or the other. They're mutually exclusive, which means we have the easier formula. We just add these two together, right? So 0.28 plus my 0.5525. What does that come out to be? 0.8325. So there's an 83.25% chance that I'll end up at one or the other. Now part D is extra credit, so that means that's for you to do and try. It's doable, but it's a little challenging. Careful, this is different. This is not equal to the probability of no grow given sun. Right? No grow given sun is our 20%. If you swap them, it's different. Just look back here at our case in the beginning of the class, right? When we had probability of A given B, we got 1/3, but when we swapped them, we got something totally different, 2/7. And so I swapped it on that problem and said, hey, well, can you come up with it? And it's doable. You can definitely do it. You just need to organize the information somehow, okay? 11's like that. This homework is kind of it's a 2-day process, so we're going to do some more notes on Monday. I'm going to stop here and just let you process some of the things we've already said, and then I'll give you some more notes on it on Monday. But start working through these problems, okay?